This is the steam engine that for 66 years powered 260 looms and practically every other machine in the factory. They were known as the prime movers because every movement of every machine in the building originated here. The steam to power the engine came from two Lancashire boilers located in the adjoining building. They were 9 feet in diameter by 30 feet long, and they required actually 3/4 of a ton of coal a day, 1,500 weight. That was shoveled manually by the fireman during the day and by the night watchman who kept the low heat going through the night. On Friday nights, when the boilers cooled, the furnaces were raked out and the fire set ready for lighting at 7 o'clock on a Sunday night in order to have a head of steam built up ready to start the engine on Monday mornings. The steam came through the steam path from the boilers and into the cylinder. This is the high pressure cylinder. It operated the piston there and then was carried to the low pressure cylinder. And the piston rod to the connecting rod to the crankshaft, which turned at 9 foot diameter, 9 ton weight driving wheel. From the driving wheel, the power was transmitted along those 6 cotton driving ropes to the driven wheel mounted in the wall. And from there, it was conveyed by a system of gear wheels, shafts, belts and pulleys to every machine and every loom in the factory. This type of connection is known as 3-bar linkage, and its function is to translate the backwards and forwards or reciprocating motion of the pistons into the rotary motion of the driving wheel. This is the governor. If, for example, a number of looms were knocked off at the one time, the engine speed would increase. Now, there is one speed and one speed only carefully worked out for a loom to work at because the timing has to be perfect. So, in order to prevent that speeding up, James Watt, the Scottish engineer who gave his name to watts in the electricity measurement, invented this system. Now, inside that cover are 3 globes, and in the same way, if you took a bit of string with a weight on the end of it and whirled it around your head, the faster you whirl it, the higher it will rise. The same thing happens with the globes, centrifugal force. If they rise to a certain level, then it automatically closes off the steam path and reduces the engine speed. It was apparently one of the first instances of a machine responding to changes in its own behaviour. These are the cams that operate the push rods that open and close the inlet valves and the exhaust valves. This is the driving wheel. You see that it's sawtoothed because it had to be levered, spoked over to bring the piston to top dead centre, ready for starting. It's sheeted in with pine boards. That was to reduce the turbulence of the air that would have been caused by the metal spokes of the wheel turning and probably 60, 70 revolutions a minute. These cams operate the push rods, which in turn operate the inlet and exhaust valves to allow the steam to enter into the cylinders and to allow the exhaust to be expelled. The driving wheel is sawtoothed off the side so that it could be levered over with a crowbar to bring the pistons to the correct point of top dead centre, ready for starting. The blueprint for the engine describes it as a 150 horsepower tandem reciprocating compound condensing engine. And I'll try to explain that in simple terms. Horsepower was based again on James Watt's formula of a weight of 33,000 pounds, say 13.25 tons. A weight of 33,000 pounds raised vertically through a distance of 1 foot in a time of 1 minute. And this machine had 150 of those. Reciprocating simply means the backward and forward motion of the pistons as opposed to the circular or rotary motion of a turbine, a windmill or a water wheel. Compound means that there are two cylinders, a high pressure and a low pressure. The high pressure, the steam entered the high pressure cylinder first of all, and then when it was used, because steam continues to expand to 600% of its original volume, the used steam from the high pressure was transferred to the low pressure where it was used over again. Condenser. Now, when steam is condensed in an enclosed vessel, it produces a vacuum. And whenever steam is used up, it has to be expelled through the exhaust valve. Now, in order to do that, which is done on the return or exhaust stroke, that is going to use up some of the engine's power in pushing out the exhaust. And James Watt came up with the invention that he would design a separate condenser in which the exhaust steam would be drawn and condensed. That would create a vacuum which would suck the steam out and reduce the power needed by the engine to push out the exhaust steam. The condenser for this engine is located immediately below the floor. Those are the steps for access for servicing. And of course that saved a considerable amount of power. The engine room itself, as you can see from the stained glass windows and the very neatly tiled floors, are resembling of a church. And in fact, Dr. Alan McCutcheon, in his book Industrial Archaeology in Northern Ireland, described them as industrial temples, which shows you the type of awe and respect that was accorded to these great engines, on which both the manufacturing of the product and the livelihood of hundreds of people depended.